In this video, we define matrix product and derive some of its properties along with lots of examples. Okay, let's start. Let A be an L by M matrix and B be an M by N matrix. So the number of columns in A should match the number of rows in B. Then we can define their product AB. Let's say its ij element is Cij. Then Cij is defined as Aik times Bkj, and k runs from 1 to m. So each ij element of the product is defined in terms of the ith row of the matrix A and the jth column of the matrix B. In other words, the ij element of the product AB is defined as this. Let's see some examples. So we have this 2 by 2 matrix, 1, 4, 2, 3, and another 2 by 2 matrix, 1, 2, 3, 4. And if you multiply them, the product is 1 times 1 plus 4 times 3. So the first row and the first column defines the 1, 1 element of the product. That is 13. And for the 1, 2 element, we take the first row of the first matrix and the second row of the second matrix, which is this, and that gives 18. And for other elements, 2, 1 element of the product is defined by the second row of the first matrix and the first column of the second matrix, which is this, that gives 11. And same for the 2, 2 element. So we have this matrix as the product between this matrix and this matrix in this order. Now let's swap the order of this matrix. So we first put this matrix first, and then we put this matrix next. And the product becomes this. So although we have the same matrices in these products, the products are different. So that means if we say this matrix is A and this matrix is B, so let's say A and B, then we have B and A here, AB is not equal to BA. So let's generalize this a little bit. Suppose we have two matrices A and B as this and this, so A, B, C, D, P, Q, R, S. Then if we multiply A and B in this order, we have this matrix as the product. On the other hand, if we calculate BA, so put this one first and this one next, we have this. And if we compare the elements of these matrices, we can see they are different. So in general, in matrix products, the commutativity does not hold, or we say matrix multiplication is not commutative. Let's see more examples. If we have 1 by 2 matrix, that is a row vector, and 2 by 1 matrix, that is a column vector, and same for C and D, then AB, so this times this. We calculate this, so the number of columns in A is 2, and the number of rows in B are 2, so we can define the product. So AB is a 1, 1 matrix, which is just a number or a scalar. And if we multiply C and D, so the number of columns in C is 1, and the number of rows in D is 1. So we can define the product, and the result is this. So A times P, A times Q, C times P, and C times Q. And next example, 2 by 2 matrix times 2 by 1 matrix. So a matrix times a column vector becomes a column vector. So the column vector is multiplied from the right, right? The next example is a row vector times a matrix. So a row vector times 2 by 2 matrix becomes a row vector. So in this case, the row vector comes to the left of the product. Next, consider a product between 3 by 3 matrices. So we have A here and B here, and the result is this. It's quite complicated. But still, we are just following the same definition. So for example, if we take the 1 element of the product, that is the first row in the first matrix and the first column in the second matrix. So A11 times B11 and A12 times B21 plus A13 times B31 and so on. Now let's see some basic rules of matrix product. So first we have associativity of matrix product or matrix multiplication. So AB times C, so that means we first multiply A and B, then to that we multiply C from the right. And this is the same as A times BC. So in this case, we first multiply BC in this order, and to that we apply A from the left. So the associativity holds for matrix product. And then distributive law, A times B plus C. So first we add B and C, then to that we multiply A from the left. And that is equal to AB plus AC. So that means we first multiply AB and multiply AC and then add them together. So the distributive law holds. And so this is distributive law from of the multiplication from the left, and the same applies for multiplication from the right. So A plus B times C is equal to AC plus BC. Now let's prove them. First, the associativity of matrix multiplication. So the ij element of AB times C is this, according to the definition of the matrix product. So AB is one matrix and C is another matrix. Therefore, their product is the ik element of the matrix AB and kj element of the matrix C, and k runs for as many times as necessary. Then we calculate this product, which is this sum. So IL element of A and LK element of B, because we are trying to find the IK element of the matrix product AB. Now let's swap the order of these sums. So put L first and K next. So L appears here and K appears here and here. So we can group the terms involving K together like this. But this one, we have BLK and CKJ. So this is the LJ element of the matrix product BC. That is this. Now look at this. We have IL element of matrix A and LJ element of matrix C. So L appears as the second index here and L appears as the first index here. That means this is the ij element of the matrix product A times BC. Therefore, the associativity holds. And next, the distributive law. So the ij element of this BC, B plus C times A from the left is, let's first calculate this product. So B plus C is a matrix and A is another matrix. So their product is defined as ik element of A and kj element of B plus C. So that's the definition. Then according to the definition of matrix addition, this is just kj element of B plus kj element of C. Now these things are just numbers. So we can apply the distributive law of ordinary numbers. Then we have this. And this is just a summation. So we can split the sum into two parts. But if you look at this, we have ik element of A and kj element of B. So that's just the ij element of the matrix product AB. And same for here. So we have the ij element of matrix AC. But according to the definition of matrix addition, this is the ij element of the sum AB plus AC. Therefore, the distributive law holds. And the other distributive law also holds, can be proved in a similar manner. So we just omit it. Next, we define a special kind of matrix called the identity matrix. An identity matrix of order n, which we denote In, or simply I if there is no confusion, is an n by n matrix. So it's a square matrix in which the I elements are 1 and all the other elements are 0. So it looks like this. The diagonal elements are 1s and everything else is 0. Sometimes we write like this. So diagonals are 1 and everything else is 0. So it's a big 0. And if we define a symbol called Kronecker's delta as this, so delta ij is equal to 1 if I is equal to j, and delta ij is equal to 0 if I is not equal to j, then we can write the identity matrix as this. So its elements are Kronecker's delta. We can write the identity matrix in this block form. So we have column vectors here. Column vector E1, column vector E2, column vector En in this way. So these column vectors are called elementary vectors. So to be more specific, E1 is this. So the first element is 1 and everything else is 0. And E2, the second element is 1, but everything else is 0, and so on. Here is an example involving the identity matrix. So we have the identity matrix of order 2 and another matrix, A, B, C, D. If we multiply A by I from the identity from the right, then we have this and we have this. So the result is A. So A is unchanged by the multiplication of the identity matrix from the right. And if we multiply the identity matrix from the left, we still get the same A. So the identity matrix does not change the other matrix if multiplied by from the right or from the left. This is true in general. So let's make it a theorem. Let A be an m by n matrix. Then we have A times In is equal to Im times A, which is equal to A. So In is the identity matrix of order n, and Im is the identity matrix of order m. So multiplying by the identity matrix either from the right or from the left does not change the matrix. So the identity matrices play the role of 1 in the matrix product, just like the ones in other number systems. Okay, let's prove this. For each I and each j, the ij element of the matrix product In is this according to the definition. So ik element of A and kj element of In. But this one is Kronecker's delta. So delta kj. So k runs from 1 to n, and delta kj is equal to 1 if k is equal to j. Otherwise, it's 0. So we can ignore all the terms except when k is equal to I. in which case this is just 1, so what remains is Aij. Therefore, the Ij element of this product is equal to the Ij element of A. And same for the other case. And we are done. Next, consider the matrix product involving the zero matrices. So let A be an n by n matrix and calculate this product, A times O and L. O and L is the n by L zero matrix. The result is the zero matrix, m by L zero matrix. And same for this one. So if we multiply L by n zero matrix and A, then we get the zero matrix. It's easy to understand because the elements of the zero matrices are all zeros, so the result should be 0. So multiplying a zero matrix from either right or from the left gives a zero matrix, so that's trivial. But here's a non-trivial example. Let's consider these matrices A and B and take their product. If we calculate this, for example, the first row and the first column, negative 2 times 3 plus 3 times 2, that gives 0. And if you calculate all other elements, they all give zeros. So even though A and B are non-zero matrices, their product can be a zero matrix. So you can see matrix algebra is quite different from the algebra of ordinary numbers like real numbers or rational numbers. Such a situation like this can happen quite often, so we give a special term for this. So let A and B be non-zero matrices such that their product exists and the product is a zero matrix. Then we call these matrices zero factors. So in this example, these matrices are zero factors because their product is a zero matrix. So let's summarize the peculiar properties of the matrix product. AB equal to BA does not always hold. So the matrix product is not commutative. And A not equal to 0 and B not equal to 0 matrix does not imply their product is non-zero matrix. So it can be a zero matrix, although neither A nor B is a zero matrix. And lastly, although we didn't discuss in detail, A not equal to a zero matrix does not imply the existence of A inverse. In ordinary numbers like real numbers, we can always divide by a non-zero number, but that's not possible in matrix algebra. So, in matrix algebra, many aspects are similar to ordinary numbers, but some things are very different. For example, commutativity and zero factors and division by non-zero matrices. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.